Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant and prepare for the future. In today's video, I would like to show you as quickly as possible a very simple and relatively small circuit that we can easily build, including with recovered components if we have enough, to build a simple charger that is somewhat universal for litiu accumulators. This circuit is essentially, which I'm also showing you right now on the screen, is essentially a controller for any kind of litiu accumulators, whether it's lithium-ion, lithium polymer, or lithium iron phosphate. This charger needs a different power supply, so he doesn't have power of his own. We need to connect him to a power supply that is able to provide a constant voltage. And this charger basically handles the constant voltage to constant current phases that are typical to lithium accumulators. And of course, we also have two potentiometers with which we can adjust the output voltage and maximum output current so that we can accommodate an entire array of accumulators that can potentially work at different voltages. This circuit, even though he's relatively small and simple, has certain advantages that other circuits that I have presented so far on my channel do not have. Before talking about this, I want to make a few I want to point towards two videos that I've created in the past. So for charging accumulators, on 18 August 2023, you can find on my channel a video called BMS, Battery Management System with Discrete Components version 2, the charger. We're gonna make a small, we're gonna ignore for the moment the term battery management system because this device is technically speaking not part of the BMS himself, but anyway, back then I showed you how we can build with moderate complexity a device that is semi-universal, is able to charge 6-volt lead acid batteries, 12-volt lead acid batteries, as well as lithium-ion, lithium polymer accumulators with a 3.7 volt nominal voltage or 3.8 volts. However, the problem of this design is the fact that he cannot accommodate lithium iron phosphate, which are a different kind of chemistry and they require different voltages, and the entire the voltage at which we need to stop is different, and since this design includes fixed steps, we cannot use this one for lithium iron phosphate. Hence my need to design the circuit, the device that I'm showing you in this particular video. I'm also pointing you towards a video that I made right before this one week ago on 11 March 2024, right? DC current monitoring circuits, options, advantages and disadvantages. Within this video, within this greater video, I made, I showed you around at the moment of 47 or 48 minutes, a circuit, and I explained to you in great details how this worked in order to measure currents with low side shunt resistors. In the design of this device that I'm presenting you in this video, I have included such a current sensing circuit, so I will not be going through all the very small details about how this circuit actually works, you can just view this portion of my previous video. I will post the link in the description down below. Okay. So in this video, we will only be able to focus on the rest of the circuit for our charger. Now, before I dive deeper into today's topic, please allow me to thank the sponsor of this video, which is PCBWay. PCBWay is a leading PCB manufacturer that can help you build your dream projects, no matter how advanced they are. They can create just the PCBs for you or help you as well solder components on them through PCB assembly services. If you're creating a full device, they can help you create a plastic case through either 3D printing or injection molding services, or even CNC machining if you need a custom metal piece for a metallic case. You're free to use your favorite design software, upload the Gerber files, and one of their professional representatives will contact you, offering you one-on-one customer service. All you need to do is go to PCBWay.com. The link is in the description. Thank you very much, PCBWay, for sponsoring this video. And now let's get started with the schematic, today's schematic, which is pretty simple and easy to create. So what we need in order to charge pretty much any kind of lithium accumulator is to be able to adjust the voltage and also the current. In practice, before we will attach the accumulator to the output of the circuit, we will use the voltage potentiometer to set the maximum voltage up to which we will want to bring our accumulator. And this might vary from a model to another model. And we will also want to use a potentiometer to set the maximum current that the circuit will inject into the first phase, which is the constant current phase of the charging process. So essentially what we have here is we need to have a 5-volt power supply, okay, connected to this controller. I'm using LM339, which is a chip with 4 different open collector comparators in the package. I'm using one of these comparators with some components around him to basically measure the current that will be drawn from the load on the output, okay? And I'm using 2 resistors, 2 shunt resistors of 100 milliohms each. I have essentially explained in detail in the previous video how this works. Like I said, I'm putting a link in the description. In order to just give you a quick reminder, I have 50 milliohms of shunt resistance here because I want to have a small voltage drop as possible. And I want to have relatively large output currents, so currents that can go up to 10 amps ideally, maximum. And at 10 amps, 50 milliohms will give us only half a volt of voltage drop, which is good enough, okay? And we have the entire circuit that basically mirrors and amplifies this voltage relative to the ground. And my idea was to have here, let me color this in magenta so you can see this better. This is the output of this current sensing circuit that I have discussed about in the last video. I wanted here to have 1 volt for 10 amps of current that flows through the entire circuit and into the load. Basically, I wanted to have 100 millivolts for each amp and 1 volt maximum voltage for 10 amps of current, so that later I can use a 1 volt reference voltage and control the rest of the circuit with just 1 volt, okay? So this is in the first part of the circuit. And then in the second part, we essentially have a MOSFET, a small driving circuit, and a couple of comparators that basically control this MOSFET and by extension control the output voltage and current. For these comparators, we need to have a sort of a reference voltage in order to use for a couple of potentiometers to control the voltage and the current. And for that, I have simply chosen two rectifying diodes in series that should give us about 1.4 volts. These are polarized with a 6 resistor here, and in parallel with both diodes, I have placed a couple of potentiometers, P1 here and P2. P1 is responsible for adjusting the voltage simply because the middle point, the cursor of this potentiometer goes into the plus input, the non-inverting input of one comparator, and the inverting input of that same comparator goes towards a voltage divider connected to the output. Basically a voltage divider that senses the output voltage and will make this comparator control the rest of the circuitry based on this output voltage and whatever voltage we set here on this potentiometer. Okay, since this potentiometer goes from 0 to 1.4 volts, but realistically speaking all we care is from 0 to 1 volts, then this voltage divider made by resistor 4 39 kilo ohm in my case and resistor 8 10 kilo ohm in my case, this voltage divider needs to divide the output voltage by a factor of 5. So on resistor 8 we need to have 1 volt, when on the output we have, so on both resistors we have 5 volts. And this is why we have these values chosen here, 10k and 39k, okay? Because we essentially have on resistor 8 we have 10 divided by the sum of both of them, which is 49. It's very close to 50, okay? So it's 0.2 or a factor of 4.9, okay? Almost 5. And in order to control, so this is for controlling the voltage, the output voltage. In order to control the output current, we have another potentiometer, again placed in parallel with these rectifying diodes that are here to just generate a reference voltage. And the middle point, the cursor of this other potentiometer goes into the non-inverting input of another comparator. Okay, and on the inverting input we have this voltage here that comes from the current sensing circuit. This way, when the current goes a bit too much, when the current goes above this threshold set by this potentiometer, the comparator will drag his output down towards the ground and will essentially close the rest of the circuit. Now, both of these comparators that control the voltage and the current, as we can see, are connected together. This is because LM339 is an open collector comparator. Okay, so he does not give us a voltage on the output. He just makes the last transistor turn on to the maximum, going to saturation, or closes him completely, and basically their output will go to high impedance. We need both of them, both of their output to be connected together, because essentially by them, either of them closing, either of them pulling their outputs down to the ground, we want to close the one and the same MOSFET transistor, which in English is called a pass transistor, because he makes the bridge between the input and the output. And by basically closing this one or opening him, we will allow more or less current on the output, and therefore higher or lower voltage. Okay. I'm going to return in a moment to this part of the circuit to explain a little bit deeper. Now I'm just gonna quickly mention this fourth comparator, because in this case, when we're trying to build a simple charging circuit, or any charging circuit for that matter, we will want to have a means to get to know when the charging process is finished, and for that we want to turn on a LED. Okay, so I have this fourth comparator here that on his non-inverting input receives the same signal, the same voltage of the current sense circuit that also gets in the inverting input of the current control comparator. Okay, for this LED comparator, this signal goes into the non-inverting input, and on the inverting input we have a voltage divider placed across the potentiometer that controls the current, but not across the entire potentiometer, just between the middle point, the cursor of the potentiometer, and the ground. And of course, these resistors need to be of a much higher value than the potentiometer himself, so as not to interfere too much. Okay, I used 100K and 2.2K. That's way more than 500 ohms, as much as are my potentiometers, so it's good enough. The idea is that on R15, on this resistor, which is tied to the ground, we want to have about 2%, or I chose to have 2% of the voltage that this potentiometer gives. And essentially this is going to be, this 2% voltage is going to be a voltage that signifies the threshold of when the current on the output has reached 2% of the current, the maximum current that we have set with this potentiometer. Okay, so for the time being, I'm considering that an accumulator is completely filled when the current through him has reached 2%. If you search on the internet, you might find that the theoretical threshold seems to be 10%. However, from a few of my practical experiments, I've seen that if we stop at 10%, the accumulator is not really recharged completely. So I have chosen to go down to 2%, okay, in order to make sure that I am recharging my accumulators better. And the idea is that when the current drops below this threshold, of course, the voltage on the minus input will be higher than the voltage on the plus input of this particular comparator, which will make the comparator drag his output down to the ground. And because his output is connected through a 560 ohm resistor and a LED towards the positive rail, the positive supply rail, then this LED will turn on, essentially. Okay, and will let us know that it's time for us to disconnect whatever accumulator we have on the output. Now, the only reason I chose 500 ohms potentiometers is because I had a couple of them that were of this value, 500 ohms. They were made of plastic. I've had some problems with plastic potentiometers in the past. They have proven to be low quality for me, so I still had a couple of them lying around and I just wanted to get rid of them. So I used them in this project, so that on the next projects I will use better potentiometers. Okay, because of course I don't want to just throw them away to the trash. Otherwise, I would have chosen much bigger values because we don't need here, you know, high currents. We just need a voltage. But of course, because I have chosen such small values for the sake of just using these potentiometers, I needed to make sure that through here flows enough current so that the diodes have, you know, enough current going through them to give us the desired voltage. And if we calculate, so we want 1.4 volts across the diodes. If we divide this by 500 ohms, we get about 3 milliamps through each potentiometer. So we have a 6 milliamps of current in only on the potentiometers themselves, and of course we need to have another 5 milliamps of current through the diode. So here in this portion of the circuit we have 11 milliamps of current. So this resistor had to be 330 ohms because, you know, we have 5 volts on the input minus 1.4 volts on the diodes. 3.6 divided by 11 milliamps, that's about 327, rounded up 330 ohms. Okay, and this is how I calculated this value. Like I said, I highly recommend that you put different value potentiometers, bigger potentiometers, and therefore you will be able to increase the value of R6 as well. And don't forget that this voltage divider, resistor 12 and 15, needs to be 20 times or bigger, preferably bigger than you know, this potentiometer over here. Other than that, we also need to discuss a little bit about this section with the MOSFET transistor and the driver circuit. Since I wanted to have a 5 volt input, okay, so maybe I should explain a little bit differently. So on the output, I wanted to charge a single cell accumulator. That means a maximum of 4.3 volts, the very worst. Okay, if I choose a litiu high, the so-called litiu high voltage accumulators that have 3.8 volt nominal voltage, 4.3 volt maximum voltage, I want them to be able to, I want to be able to push through them several amps of current, ideally 10 amps or as close as possible as 10 amps. Okay, this leaves me and at the same time I wanted to have as small heat generated, so a small heat dissipated by this transistor here. In order to accomplish this, I needed to use a 5 volt, and I also wanted to use a 5 volt power supply because I have several of them that are you know, pretty strong, 5 volt 10 amps or so. And also because you know, we can just take a power supply from a desktop computer that has 5 volts, 12 volts and some other voltages, and we should be able to just use a computer power supply to power this entire circuit to charge our accumulators. So I couldn't use here as a pass transistor bipolar transistor because those have to drop a lot more voltage. MOSFET, on the other hand, will, if he's open to the maximum, he will act like a resistor, and a quite small value resistor. So the voltage drop across him should be pretty small. I chose LiFePO4, which is a bit unusual. I think it's quite an old transistor. We can still get him, we can still find him on the market, but anyway, I chose this model because I had a whole bunch of them bought very, very, very cheaply. A second-hand transistors that I bought very cheaply from someone who recovered them from some power supplies. And because I had such, you know, it made sense for me to use such a model instead of others for which I had to pay more, and I have fewer pieces of them. This MOSFET is pretty decent, has 55 milliohms of 55 millivolts of 55 milliohms of resistance drain to source when he's turned on to the maximum. This means that if we pass 10 amps through him, we're only gonna have half a volt or a little bit over half a volt of voltage drop. This is perfect because this goes very well with our very low headroom here between the input and the output. And also this model of MOSFET can deliver a continuous maximum of anywhere between 29 and 46 amps on the output, so it's way more than I plan to use. Okay, so this way we are basically solving multiple problems at the same time. We are able to use a small voltage on the input that's a lot closer to the voltage that we will have on the output for the accumulator. We will therefore have a much smaller dissipation power, and you know, everything's gonna be nicer than with a bipolar transistor. However, we need to you know, drive this MOSFET with another circuit, and for that we have this push-pull configuration with two bipolar transistors, just small power, nothing fancy, BC 547 and 557. Okay, which are they have their bases tied to the outputs of the two comparators that perform voltage and current regulation. Their emitters are connected through a resistor to the gate of this MOSFET. I have established through basically experimental multiple tries experimentally that 3.3 kilo ohms seems to be a good enough resistance, even though she seems a bit too high, but for this particular project was good enough. Okay, and in order to turn on this transistor, we sadly need to have a higher voltage, because we cannot use the same 5 volt from the input, because we need to have 5 volts higher than the input in order to, you know, properly control this MOSFET, even when he is turned on and his source essentially is at the same potential or very close to the same potential with the drain. Okay, and for that we need to power these the NPN transistors collector and this resistor 5, which is polarizing this transistor, and they need to be connected to a different point that has a higher voltage, a point that I've named overvolt here. Okay, and if we use a computer power supply like I'm going to show you in a moment, this can be done pretty easily by using the 12 volt rail of that computer power supply. Okay, and that's pretty much it, the entire circuit. I've also placed a large filtering capacitor on the output so that I can you know, make the variations, I can prevent the oscillations of the circuit, because MOSFETs tend to I mean, such circuits tend to oscillate when we are using MOSFET transistors here. This is why the gate has such a high value resistance, and I've also placed you know, a high value filtering capacitor on the output. In practice, you could try with a much smaller capacitor, and you know, I'm guessing a smaller value of resistor. It depends. For me, 560 microfarads was good enough and offers good stability on the output. Also, because of this high capacitance on the output, whenever we are adjusting the output voltage, the output tends to drop a lot slower than we might like. So I have decided on the outside to place a 180 ohm resistor between right? The two output connectors, so that I can discharge this capacitor a little bit faster when I have no load whatsoever. In practice, you can just make this resistor divider 4 and 8, make these two resistors smaller, and you can get away with that just as easily. And this is pretty much the entire circuit. It's not rocket science, it's not that big of a deal, but you know, it gives us the option of selecting whatever voltage we want and whatever current we want, and not have just a few discrete steps, but have actually an entire infinity of values to choose from. So now let me show you how the circuit works and what are his performances. Okay, so here I have on the right the charger is placed in this transparent plastic box that I got from some chocolate cookies. Okay, I typically like to do whenever I need something quick and simple. I like to reuse plastic boxes from other things, and also as input-output connectors, I have used just some M4 screws and nuts. On the far left side of the screen, we can see a computer power supply, a very simple, very cheap computer power supply. Okay, and we are using, of course, the ground level, the ground pin, but also the 5 and the 12-volt pin to power our charger. As we can see on the right side, on the right upper side, we have one blue with black cable and a couple of red with yellow cables. Okay, in the center left, we have a small black multimeter set to measure the output voltage. I have nothing connected to the output whatsoever, and I also have a portable oscilloscope on the output set to AC coupling, in order to see you know, how much noise and ripple I have. And as we can see now, we have 0 volts on the output, so we can clearly bring down the output voltage to 0 volts, something that we might not be able to do in other circuits, in other topologies. And the scope meter, the portable oscilloscope, is set to 20 millivolts per vertical division, and for the most part we see that we have about between 1 and 2 divisions of noise and ripple, okay, regardless of the output voltage. And this is pretty decent. Okay, it's not super great, but remember, we are, technically speaking, not going to use this power source you know, as a lab power supply, even though we could. I mean, there's nothing stopping us, but this circuit is designed and meant for charging accumulators. Okay, and I have slowly increased the voltage here to show you that this is a possibility and that we have a fairly small ripple on the output. Okay, and I am slowly going up to 5 volts. I'm gonna skip a little bit. Okay, so now let me show you charging a 2.9 amp hour accumulator. So now in this video, I have placed this multimeter across the shunt resistor, and what we're seeing here are the millivolts on the shunt resistor. So essentially, I wanted to show you the current that we are able to, you know, push towards our accumulator. And here I'm showing you that I have one of these models of 18650 lithium iron accumulator, lithium-ion accumulator that have 2.9 amp hours. That dash 29E at the end signifies that it's a 2.9 amp hour rated accumulator. And now I'm connecting him to the output of this charge controller. Okay, and the current goes straight to 8 amps because, yeah, my current potentiometer was not adjusted correctly. So when I say 8 amps, since we have 400 millivolts across 50 milliohms of shunt resistance, you know, you can easily divide this and find, or it's easier to just multiply this number with 20. Okay, so 400 millivolts multiplied by 20 means 8 amps. 8 amps was a bit too much, so I started adjusting my current potentiometer and I brought him down to about 2 amps. Right here. Okay, around 100 millivolts means 2 amps of current. And this is pretty much how you do it. You first use the voltage potentiometer to adjust the output voltage to the maximum rating of your accumulator. That is before you connect the accumulator, and then you connect the accumulator and you take a look at the current and make sure that the current doesn't go overboard. I wanted to also make a few checks to see if I still have around 5 volts on the input, and I do. Okay, and then I went to the output voltage and I measured, and this accumulator was relatively discharged, so he had about 3.6 volts, but you know, over time this voltage would have increased. I also placed the scope meter to check noise and ripple, and we still have 20 millivolts per vertical division, and we get to see pretty much the same noise and ripple as before. Okay, it's not great, but again, for just charging an accumulator, we don't care about the noise and the ripple. This is a huge advantage. So that's pretty much it in terms of what I wanted to show you today. Again, it's a simple circuit. It can be pretty easily created. I'm going to put on Patreon the files to build this, both the schematics, the electronic schematic, as well as the PCB schematics. As you can see in this presentation video, I haven't bothered with an actual printed circuit board. I've just used a perforated board and made the connections via wires. This is also good enough. The circuit will work pretty well nevertheless. Okay, and another thing with the MOSFET, you don't need to use this model of MOSFET. You can use any N-channel enhancement mode MOSFET. Pretty much pick whatever you want from the market, as long as he is able to pass enough current for you, preferably more than 10 amps, he will be good. Of course, he needs to be mounted on a radiator, on a cooling radiator, because he will hit during some charging processes, depending on the current that you will want to have on the output. Of course, he will not hit very much, but he needs a radiator. He cannot cool himself all by himself. So yeah, all in all, this is pretty much it. I find this useful, especially since I can adjust the voltage as I like. I have charged so far a bunch of relatively small lithium iron phosphate accumulators that can go up to 3.65 volts. And I have also charged a very large 280 amp hour lithium iron phosphate cell that can only go up to 3.4 volts. Did the job pretty well, so I am pretty happy with this design. Of course, this design could be improved, and this is probably something that is definitely going to happen in the future. So for the time being, thank you very much for watching this video. Thank you very much to those who are supporting my work on Patreon. Link is in the description for anyone else who is willing to support my work. If not, for free, a like and a subscribe to my channel definitely helps the YouTube algorithm possibly recommend my videos to other people who might benefit from them. So again, thank you very much for watching this video, and I hope I will see you soon in the next one. Bye bye.